All right, good morning.
Good morning.
All right, hope everybody's doing well. Any questions from yesterday or from Monday? All right, well, let's start off by talking about structures in C. So in 121, you encounter a struct statement, and we don't really use it a lot in 224, but we're going to use it very heavily in this course. Let me give you a possible motivating example for where structures come into play in programming. So let's suppose you're writing a program that's processing some sort of data. So suppose, for example, you want to monitor network traffic. And so you're going to collect information periodically about what's going on with your network. So you want to know, how much information has been sent, how much information has been received, how many people are on the system right now, and the current time. So we want to record this information and save it, and then do some statistics or generate some reports or things like that. So let's just let's simplify it down to 3 pieces of data. So the amount of traffic, which is an integer, right? So the amount of stuff received and sent. The number of users, which is just how many people are on the system right now, and an integer time, which could be, number of seconds since the beginning of time, or it could be, an hour number with a day of the year number or something. But let's just suppose it's codable as an integer. And so you have something running which, every hour or something is going to wake up and record this information. And then we're going to do some processing on it. Well, when we have a collection of information we want to store, typically we store it in an array. Because arrays, we can just keep bumping up the index and adding things to the end of them. So these might be, really large arrays. And let's suppose we're expecting no more than 1,000 samples. And we're not too worried about conserving memory. So we'll just make a set of 3 arrays that hold, each piece of information. And we'll have, an integer called samples, which will initialize to 0. And then every time that our process runs and wants to record a new piece of information, we'll store the amount of current traffic, number of users, and time into these arrays using samples as an index, and then we'll increment this index. So the first sample we take will get stored at traffic, num users, and time brackets 0, and samples will increment to 1. The next time we take a snapshot, we'll store them at elements 1, and so on. This works great, right? We can do this, no problem with this. This is a approach that's loosely called parallel arrays. And we have 3 arrays storing 3 different types of information. Well, this works well, but there's a few inconveniences here. The first inconvenience is this is a lot of information to move around, right? If I want to generate statistics on this, I can call my statistics function. I have to pass it traffic, num users, time, and samples. Right? We always need samples because there's no way to tell how much stuff is actually in these arrays unless we have, some variable that's keeping track of that. So I can call my statistics function and I pass it 4 arguments: traffic, num users, time, and samples. And if I want to generate a report, I can call my report function and pass it 4 pieces of information: traffic, num users, time, and samples. And every time that I'm working with this collection of data, I have these 4 things I have to pass around. And I have to keep them in the right order Because if I accidentally, use time, traffic, num users, code's not going to notice. I'm just going to get weird results. So that's one inconvenience slash potential error avenue, is just having, multiple variables I have to pass around. The other issue is we have to keep these arrays in parallel. So suppose I want to sort this collection of data by the number of users, so that I can make a graph of, number of users versus amount of traffic, right? Well, I can go in with a bubble sort or something, and I can sort this array numerically. But as I'm sorting it, I need to keep my traffic and time arrays sorted in sync. So if I swap the first two elements of my num users array, I have to swap the first two elements of my traffic and time array also. And so with parallel arrays, we're forced to preserve this parallelism. And that's inconvenient, that's error prone, and it means that if I add some new piece of information to the mix, like I suddenly want to record, something like memory usage, while I make another array of memory usage, I have to go through all my code, and any time that I manipulate any of these arrays, I have to now do that manipulation to my memory usage array. And all my calls, when I call my statistics code, now I have to pass it in my memory usage array as well. And it's not conducive to code maintenance and robust development. So we'd like to get away from parallel arrays, and the most straightforward way to do that is by using a structure statement. So we can define a structure as basically a new type of variable in C. So struct is a keyword, and it's followed by the name of the structure that we want. So I'm just going to call my structure data. And I'm going to say data consists of the following fields, the following pieces of information. A single integer, which shows me, how much network traffic there is. An integer, which tells me how many users are logged in. An integer, which tells me the current time. Close curly bracket, gotta have the semicolon. Alright, now I have a new type of data called a struct data, and I can make a single array like this. Struct data readings, bracket 1000. And I'll keep my samples. And now, a single element in my readings array is a variable of type struct data, which means it has a traffic, a num users, and a time field. And if I want to look at, element I of my readings array, I could say readings bracket I, and this is a struct data. Well, a struct data is comprised of three different pieces of information. If I wanted to know what the traffic was in this piece of data, I can say readings bracket I dot traffic. Right, so the dot says I want this field from this struct data. And I could do dot num users dot time to get to the other fields. So this helps with our two disadvantages of parallel arrays. Number one, all I really have to pass around is this readings array, right? And if it's an array, I need to know how big it is. But if this has 50 different fields in it, it's still just, this one array. Yeah, these are comparable to classes, exactly. So we have this one variable which has all this other type of information contained in it. So that simplifies, our calling of functions, our writing of functions, and if I add more fields to this, it doesn't change the call to the function. I'm still just passing it, an array or an element of this type. I is just a bogus variable. I'm just doing an example. The other thing that this helps with is if we're doing, for example, a sort, right? If we swap two elements of this array, well, each of those elements contains all these pieces of information. So if you swap these, right, we're swapping all of those pieces of information. So we don't have to worry about maintaining these parallel arrays by hand. It's kind of done for us. And so you know, I was just imagining some loop where we're iterating on I or something here, but you know, if you have a struct data variable called blah, right, we can say blah dot traffic or blah dot time, etc. Right, so this is how you access the pieces or the fields of that structure. And so this is preamble to CSE223 when we talk about object-oriented programming. So in 223, instead of talking about a structure, we'll talk about a class. And a class really is like a structure. It defines different fields associated with, you know, an object of that type, but it also lets us throw in code. So we can have more than just, you know, integers and characters and strings. We can also have pieces of runnable code that are part of the structure. When you do that, now you got what's called an object, and that's what a class is. You can put structures inside structures. So I could have a struct, you know, some other type of thing, and have that be one field of my struct data. And we will do that a lot also. So this is a really powerful mechanism. So yeah, in C you can't put methods or code inside structures. Not directly, you can fake it, but it's really just data. When we start putting code into our structures, then we're talking about objects and classes and object-oriented programming. So this is a powerful construct, right? Even with just data. For collecting pieces of data that logically belong together and treating them as a single entity. Now, the trick to using a structure is, you know, if I define a structure named data, then struct data, 2 words separated by a space. Struct is a keyword, space, the name of the structure. This is a new type of variable. I can use it to declare a variable. I can use it to declare an array of variables. I can use it as a return type from a function. I can use it as an argument to a function. I can use it inside a size of call. I can use it wherever I could use an int or a float or a double or any other type of variable. So it's a new type. It's an extended, you know, version of C now that has this new type of thing. But typing struct space data, struct space data, struct space data can get to be kind of a pain. Not a huge pain, but you know, a bit of a pain. So so there's a typedef statement that we can use to simplify this, and the typedef statement looks like this. We can say typedef, we can put in the name of an existing type, and we can give it a new name. So if I don't like integers, if I want my integers to be called Bob, right, I could say typedef integer Bob. And now I can use Bob as the name of an integer. So we use this typically for structures. And we can say something like typedef struct, what do they call this thing? Data? Struct data. And whatever I want to call it, whatever kind of variable I want. So I might call it, typical thing I might do is make it uppercase data. But I could call it, you know, monitored data or reading info or you know, George Jetson or whatever. So it's just a shortcut. It doesn't do anything that we can't do just by saying struct data all the time. But once I've done this, then I can say something like, you know, data readings bracket 1000. So it's a nod to readability, basically. Typedefs have to go after the structure statement, because if you do them before, the compiler doesn't know what a struct data looks like. I think. Certainly doesn't hurt to do it after. So that's sort of the mechanics of defining structures and using a typedef in C. Questions about that? All right, so we're going to change gears for a few minutes. We're going to talk about order of complexity. And the reason I'm talking about this is we're going to discuss what order of complexity means, which is it's basically a way to analyze algorithms. And then I want to take that mindset and start analyzing basic algorithms that we use for processing data in arrays. And I want to see what works well with arrays and what could be improved. And thinking about that, about how we can use arrays and work better with them, is going to lead us into our first full-on data structure, which is going to be a linked list. And linked lists are what we're going to do for basically the next 2 weeks. So I want to put some motivation in here to lead up to this. So order of complexity. And when you study, a course in algorithms, you'll talk a lot about order of complexity. This is often called Big O notation, and we'll see that in a minute. But the basic idea here is we can ask how long a program takes to run, but that doesn't really give us a full. That's not the full story on the algorithm or the program, right? Somebody might have a program that takes a minute to run. Somebody might have a program that takes a second to run. Which program is better? I have no idea. If the program that takes a minute is picking winning lottery numbers, I'd say that's a better program than a program that takes a second and tells me what time it is right now, right? So the amount of time a program takes is not really a good measure of how good the algorithm is inside the program. Right? We need to compare algorithms in some sort of meaningful way. So suppose we're sorting numbers, right? So this is something we do a lot of. We have a set of numbers in memory. We want to organize them so that they're arranged smallest to largest. Well, if you have a few numbers, you can sort them pretty quickly. If you have a billion numbers, it's going to take longer to sort. So to compare two sorting algorithms, we kind of want the same amount of information, right? We want to both be, sorting a million numbers with both algorithms to compare those. But that's still not the full story, because actual time that it takes to run an algorithm is not as meaningful as you might think. Suppose my algorithm runs in, 10 milliseconds. But I'm running it on an operating system that takes, 10 seconds to start executing my program. So I click on my program and it takes 10 seconds for the drive to spin up and the OS to find the file and to load it in and all this. And it looks like it takes 10 seconds to run my program. And maybe there's a different version of this algorithm running on, a different operating system where the program starts in 1 second. Maybe that program actually runs for 5 seconds, so it's a lot slower, but I get my answer in 6 seconds instead of 10. So looking at the time that it takes a program to run is not necessarily meaningful. Because in that last example, my program, which runs really quickly, well, the total time it takes is being dominated by the 10 seconds it takes the system to start it. But if I ran this program on a lot more data, right, so that it was taking an hour, that 10 seconds to start wouldn't really affect my final time. But that other algorithm, which looked like it was quicker, now it might take, 100 hours. It's going to be clear that algorithm is worse. So what we want to do is we want to find some way to analyze the performance of algorithms that get away from details like, how fast is the machine that it's running on? How much overhead is there to start this algorithm? How much overhead is there to finish it? We really want to get down to the guts of the internal processing of an algorithm and see sort of how that measures out from one algorithm to another. So order of complexity is based around the idea of looking at required time compared to the amount of data. And we're going to look at how the time required for an algorithm changes as the amount of data changes. So we're going to say, you know, I don't care if it takes an hour or a minute to process this much data. What happens when you double the amount of data? Does it go to 2 hours, 2 minutes, or does it go to something much bigger? So let me give you some possible examples. So here's the amount of data, and here's the time. So suppose we have 10 pieces of data, and it takes 10 seconds. And suppose that we were to double the amount of data, and we find that now it takes 20 seconds. And when we triple the amount of data, we find that it takes 30 seconds. All right, this is what we call linear. And an algorithm that's linear, we say that's order n. And we write that as a script O followed by an n in parentheses. And we read that as order n. Now let's say I run this on a faster machine. Let's say I have a machine that's twice as fast. So to process 10 pieces of data takes 5 seconds. 20 pieces takes 10 seconds. 30 pieces takes 15 seconds. Even though this machine is faster than that one, the way in which the time increases relative to the amount of data is still linear. When I doubled the amount of data, I doubled the amount of time. When I tripled the amount of data, I tripled the amount of time. So this is still order n. And this is the idea of using this big O notation, is that it sort of weeds out the specifics of how long it takes to actually run something. It's looking at the increase in the amount of time required as the data size increases. Let's say I make some change to my program, and now my program runs 5 times faster. So my algorithm seems like it's 5 times faster than it was, right? I rewrote it in assembly language, and I got rid of some things, and now it's a 5x speed up, right? So now, instead of taking 5 seconds, it takes 1 second. Instead of taking 10, it takes 2. Instead of taking 15, it takes 3. This is still linear. Doubling the amount of data doubles the amount of time. Tripling the amount of data triples the amount of time. It's still order n. So yeah, this will eventually lead us to P versus NP in CSE215, or it has in the past. Recursive regex, that would be interesting. Calculating order of complexity is not always straightforward, and it would be interesting to do it on a regular expression. It'd be cool to see what it comes out as. All right, so order of complexity is not fooled by you know, running on a faster machine or making you know, linear speed ups to your algorithm. Let me show you a different order of complexity. Suppose I can process 10 pieces of data in 1 second, and suppose processing 20 pieces of data takes me 4 seconds. And suppose processing 30 pieces of data takes me 9 seconds. Well, this is worse than linear performance. Right? when I doubled the amount of data, my time went up by 4x. When I tripled the amount of data, my time went up by 9x. So my time is increasing by the square of the increase in the amount of data. And we say this is order n squared. Or we might say this is quadratic performance. Order n squared, not very desirable, but fairly common. So let's look at a bubble sort. So we've done bubble sorts in 121, I believe. What's the basic idea? You have a set of data, and we want to arrange it from smallest to largest. So we make a pass through the data, going from, say, 1 to n if we have n pieces of data, and we compare and swap each element with the element after it if it's in the wrong order. So 4 is smaller than 2, so we would swap those. 4 is bigger than 2, so we swap. 4 is smaller than 7, so we leave it. 7 is smaller than 19, so we leave that. 19 is bigger than 3, so we swap that. 19 is bigger than 6, so we swap those. 19 is bigger than 5, so we swap. 19 is smaller than 28. 28 is bigger than 8, so we swap those. And after this first pass through our data, our largest number is in the bottom of our array. And then we do this whole thing a total of n times. Because each time we make one of these inner passes, one more number comes into the right position. And so if we have n pieces of data, we need roughly n passes. So that's a basic bubble sort. Order of complexity, n squared. And you can see it by looking at your nested loops. This inner loop is going to take n operations. Right? You may not actually swap every time through, but that's a nuance. That's a constant factor. We're going to have to loop a total of n times and compare, element I to element I plus 1. If they're out of order, swap them. So this inner loop takes roughly n operations, and we do that inner loop roughly n times. So this inner piece gets done a total of n squared times. So bubble sort is a classic n squared algorithm. And n squared is not very nice because if you double your amount of data, it takes 4 times as long. If you increase your amount of data by 1,000,000, you increase your sort time by 1,000,000,000,000, right? 1,000 billion, which is a huge increase in time. Even if your sort was really fast, increasing your sort time by 1,000,000,000,000 is not a good day. All right, so we pay attention to order of complexity. Now there's nuances in here. For example, a well-written bubble sort won't necessarily do this inner loop n times. It might make note of whether or not something got changed on this inner pass, and if nothing changed, you don't need to do any more passes. So if your array was almost sorted to begin with, it may be you do 2 or 3 of these inner passes, and the next time through nothing gets rearranged, you're done. And so while this inner loop takes order n, the outer one might take only 1 pass, it might take n passes. On average, it might take n over 2 passes. But again, cutting down your total time by a constant factor doesn't change your order of complexity. You might also use an embellishment that, once we've gone through one inner pass, we know that this number is in the right spot. The next time through, we don't have to go up to n, we have to go up to n minus 1. And then we'll have two things in the right spot. The next time through, we have to go up to n minus 2. And so instead of n squared, this is going to end up being something like order n times n minus 1 over 2. But it turns out when n gets really, really large, this is going to be the same order of complexity as n squared. So when we deal with order of complexity, we can throw away usually smaller terms. We can throw away constants. We just look at the term that kind of dominates the whole expression. And we'll do this a lot more when we talk about sorts. We'll spend about a week talking about different sort algorithms. And we'll get into more of the details of order of complexity. But for now, let's just use this as a motivating example. And there are better orders of complexity. So n log n. There's sort routines that have that complexity. So quick sort, heap sort are two that come to mind. And this is nice because if you increase your amount of data by 1,000,000, n log n goes up by 20 million. It's not a huge factor. It's certainly better than a million, which is a trillion. Better order of complexity yet is log n. This will be what we end up with when we get to binary trees for doing search and insert, which is the journey we're starting right now. This is constant time complexity. This is an algorithm that always takes the same amount of time, no matter how much data you have. And that's a really sweet spot. It means if it takes this much time to process, a certain amount of data, if you had 1 trillion times as much data, it would still take this much time. So the classic example of this is a hash or an associative array, as someone just said in chat. And that has a theoretical performance of order 1. So those are useful. We'll study these, we'll build these up, and we'll do programming assignments on them. And then there's the order 0, which is, an algorithm that takes no time no matter how much data you have. And I think this is what the universe is. And then in the last section, somebody suggested order -1, where you actually get time back by running this algorithm. So I offered to let them do an SLP on that if they can turn this into a time travel machine. So we'll see if that happens. All right, so what do we do with this? What I want to do is I want to look at some algorithms for processing arrays. So we're going to think about, an array of data. So there's an array of numbers. And I want to think about different things that we do with this array. So for example, we may want to add an element to an array. We may want to delete an element from an array. We may want to search for something in an array. Order of sign n. That would be like having somebody work for you and they're very susceptible to their biorhythms. And maybe something like that. That would be interesting. I think I could think of an order sign n algorithm. Because you can generate primes using sine waves, looking at constructive interference of sine waves with prime periodicities. Anyway, so let's take an array of numbers, and let's say we want to add another number to this array. What's the easiest way to add another element to this array? This is just, some integer data. And, they're stored in here, and I want to add the number, 11 to this array. What's the least amount of work I could do to add an 11 to this? Append, right? I'll just put it down here at the next location in the array. I'll bump up this counter that says how many things are in my array. And it doesn't matter if I have 5 things or 50,000 things in here. Assuming I have space in my array, I just store this in the next location. So this is order 1. But this is an unsorted array. Right, the data is clearly not in order. Really, really fast to append. What if I want to delete something from the array? Order 0 and speed of light could be related. Suppose that this is my array and I want to delete the number 5 from here. How would I do that? Right? Search and delete. Before I can delete a number, I have to find it. So let's talk about search. How long does it take to find something in our array? Basically takes n operations, right? Because if I want to know if the number 5 is in here, really the only thing I can do is just start at the beginning, are you a 5, are you a 5, are you a 5, are you a 5, and eventually either find it or get to the end of my array and say it's not there. So this is going to be an order n operation. Now I might get lucky and I'm trying to search for a 2 and hey, it's the first thing in my list. I might get unlucky and be searching for an 11 or searching for something that's not on my list and I have to go through all n. So average would be n over 2, but remember order n over 2 is the same as order n. So this is linear for search. And then deletion is pretty much going to be n operations. And here, if I happen to find something in the beginning, I could delete that. How would I delete something from the beginning of my array? If I want to delete the 11 at the end, I just, say, yeah, I have one fewer thing in my array. How could I delete the first thing efficiently? I could replace the content with a null, but that's going to make things a little tricky down the road, and they're going to lose that space, and eventually that may be a problem. I could move the starting point, but that's going to be trickier than we want to do. I could shift the array. I could move the 4 up to here, the 3 up to here, and so on. That's going to be an order n operation. Any other ideas? Move the last one to the front. I like that. Right? If I want to delete the 2, I could just take this 11, put it up there, and then say I've got one fewer elements in my array. It's not sorted, so I don't care if I change the order. That's an order 1 operation. But it's still order n to find the thing you want to delete. So any of these approaches that I've seen in chat will work, but they're all going to end up being order n. Okay, well that's not horrible. It's not n squared, but it's not as great as we would like. So so suppose my numbers are sorted. So suppose my array looks like this. It's a sorted array. So how long does it take to search for something in a sorted array? So I can definitely still search in order n, right? I can start at the beginning and just go through and look until I either run out of numbers or I find my number. But I can do better than that. Say I'm searching for the number, I don't know, let's search for the number 4. Right? What can you do? You can start in the middle of your array and say, is that the number 4? If it is, you're done. You got lucky. If it's not, you can say, is this bigger or smaller than what I'm looking for? Well, 12 is bigger than what I'm looking for. I don't have to look at any of these numbers. Because if 12 is bigger than what I want, all these other numbers are also bigger. So I throw away half my data, and now I'm searching a much smaller array. And I'll start at the midpoint of this. Let's say it's a 3, and I can say, is that the number I want? No, that's actually smaller. I don't have to look at anything in this half of that subarray. And now I've got a smaller list, and I'll pick the midpoint, and let's say it's a 4, and I say, yeah, there's a 4. This is a binary search. This is our high-low game from 224, right? When you play high-low, somebody thinks of a number from 1 to 100. You could certainly guess it in 100 tries. That would be an order n search. But if we know about, numbers being ordered, and we're allowed to find out if our guess is high or low, we can do this constant subdividing in half. If we guess 50 and they tell us 50 is too small, we don't need to guess 1 through 49 or 50 again. We've got a smaller problem trying to guess a number between 51 and 100. So this is high-low. And it leads to a search time, which is log n. Log n because, right, each time we make a guess, each time we check something, we cut our list in half. And this continues until we find our number, or we've cut our list in half so many times that it contains only a single thing. And that's either our number or the number's not found in there. So how many times can you cut something in half until you get to 1? That's what the log base 2 tells you. So if that doesn't seem apparent to you, play around with it, right? Think about cutting things in half and how you can cut things in half until you get down to one thing, and see if you can convince yourself that the number of times you cut it in half, if you multiply 2 that many times, you end up with the original number of things. And we'll pop into log n's, the rest of our programming careers. So it's a good thing to play around with. So search is order log n. How about adding to this array, though? How long does it take to insert our 11 into this original array? So there's our array. Where does the 11 go? So we need to search to find out where it is. That's going to be a log n operation, right? And then we want to store, so we find out that the 11 should go here between the 8 and the 12. How do we put the 11 in there? Move everything up. And we really have no choice. Right? If we try to add an 11 to this, it's really got to go into here. It should be a data bracket 3.5 or something, right? And we can't do that. There's only one possible place in memory where the number after 8 can be stored, and that's right here. So our 11 has to go there, which means we have to move the 12 down, which means the 16 and the 19 and the 25 have to get moved down. And so depending on where we're inserting, this ends up being an order n operation. So it's log n to search and then n to insert, and the n dominates this expression. So this is asymptotically order n. Technically log n plus n. But if n is up in the gazillion range, log n is so small, it's like a gazillion plus, change. So this is basically log n. And deletion is kind of the same thing. It's going to take log n to find it, and then when you remove it, you have to shift everything up. So that's still going to be log n. All right. So this is this memory map from yesterday where we had an array and we looked at where those elements of the array were stored. So if our data array starts at some base point and ints take 4 bytes, then data bracket I is stored at memory location base point plus 4 times I. So if your integers take 4 bytes and your array starts at this address, the address of element I is that address plus 4 times I. Okay, that's direct memory location arithmetic. And this is what the compiler codes up when you have something which uses data bracket I. It takes the address of data's first element, it adds 4 times the index, and it uses that as a memory address to access this piece of information. Yeah, so comment in chat, yeah, maybe log n plus n over 2. The n over 2 kind of depends where you end up with, right? If you find your number is down here at the end, you know, you're inserting 36, you don't have to move anything. If you're inserting a 1, you have to move everything. So average would be n over 2, which is the same as order n. All right, so we have this pointer arithmetic that we do, right? And this forces us to say, you know, if the number 8 is element 3 and we want 11 to be element 4, this is where element 4 has got to be stored in memory. There's this rigid association between the elements of this array and where they're stored in memory. And that's why we get this undesirable performance when we try to add something. Because we can't actually sandwich something in between the 8 and the 12. So we can improve this by doing something pretty clever. Right now we have our data looking like this. So 2, 3, 4, 8. $12, $16, $19, $25. Well, the difficulty with inserting efficiently is that, you know, whatever comes after 8 has to go right in here, and that space is occupied. Well, here's a different idea. Suppose that instead of storing just a piece of data, we also stored where the next piece of information was going to be located. So we store data as a 2, but we also store the following piece of information. The next number in our list is stored at index 1. And at index 1, we store a 3, and we also say, hey, the next piece of information is stored at index 2. And the 4 is the next piece of information, that's followed by the number at index 3. 8 comes next, and that's followed by the number at index 4. And this is, you know, kind of silly looking. But this captures, you know, the same information as our original array. But it has an advantage. The advantage is if we want to insert something right here in between the 8 and the 12, it doesn't have to go at index 4. We could take our new number 11, put it down here at element 8, and all we have to do is the following. Element 3, which is an 8, instead of saying this should be followed by the 12, this should be followed by the thing at index 8, which is an 11. And the 11, instead of being followed by whatever's down here, should be followed by this number 12, which is up here at element 4. And so we are building a collection of links like that. And so this is the linked list, right? We start at the 2, and in addition to having the actual piece of data, we have something which tells us where the next piece of data is located. So 2 is followed by 3, which is followed by 4, which is followed by 8, which is followed by 11, which is followed by 12, and then 16, and 19, and 25. And it's going to turn out with a linked list. Once we know where we want to insert the data, it's going to be order 1. But it's still going to be order n to find that piece of data. If we want to delete something, we can delete also in an order 1, but it'll take order n to find, and search will take order n. So this looks worse than an unsorted array, but this is a setup to what comes next, which is binary trees. And trees are going to be order log n across the board. So we're going to play with linked list for the next couple of weeks. And we'll spell this out in more careful detail tomorrow. We'll work through some examples, and then we'll start talking about your first big programming assignment, which will be implementing a linked list inside an array using structures for each element. All right, so that'll be your first programming assignment. And that will lead to the second programming assignment, which will be a linked list dynamically allocated in memory. Is there any added pointer to the structure that would, in addition to the O1 insert, would have O1 lookup as well? We won't get to O1, but we'll get to order log n, and that'll be a binary tree. And that's really just a linked list with added machinery to do efficient lookup. So we'll get there in about 3 weeks. All right, cool. Have a good one. I will see you next time.